of this black region here. A little complicated region. Okay? Now, when lambda is 0, right, our map is just z to the n, so the Julia set is just the unit circle. All points outside in the circle go to infinity, everything inside goes to 0. That's pretty simple. But as soon as lambda is non-zero, boom, the Julia set explodes. One reason is we go from a degree n polynomial to a degree 2n rational map. The degree goes way up, but you see the Julia set goes crazy. Well, you don't see any black here, but if the eye goes from red, orange to yellow, maybe you see some green in here. There's actually a small thin filament of black. Think of this yellow region as being the outer boundary of the black region. This Julia set is a Sierpinski curve. If I choose a lambda, and here I just should say, here's our base of infinity, here's the neighborhood of 0 of the trapdoor. If I let lambda be much smaller, there's the Julia set. Looks very different, but again, this is a Sierpinski curve. And again, another lambda value, the Julia set's a Sierpinski curve. Okay, and these Sierpinski curves arise in all sorts of different ways in this family of maps. For example, if the critical orbits eventually fall into the trapdoor, meaning the critical points map to the critical value, and then after iteration 2 or more, the critical value falls into the trapdoor, then the Julia set's a Sierpinski curve. Like for example, this is the case n equals 2, there's actually 4 critical points here, so to see 4 figure 8 regions. Critical points map to the critical values, then map into the trapdoor and go off to infinity. So if the critical points take 2 or more iterations to go into the trapdoor, then automatically the Julia set is a Sierpinski curve. Okay. And there's all kinds of ways this happens. This is the parameter plane for the family lambda z cubed plus lambda over z cubed. Okay, you see lots of red disks there. Those are what we call Sierpinski holes. You take any lambda value in one of those holes, the corresponding Julia set is a Sierpinski curve. Move to that hole there, Sierpinski curve. Different looking set, still homomorphic to the carpet. Again, different looking, but still homomorphic to the carpet. All sorts of different ways that Sierpinski carpets arise when there's escape time critical orbit. And now think about it. How do you show that this set is homomorphic to that set if we've got an escape time Julia set? It's easy. All we have to do is verify those 5 conditions. We have to show that this set is compact and connected. But now remember, all the critical points are eventually landing in the trapdoor and going to infinity. So that means all the Fatu components of the basement of infinity and all of its pre-images, all open disks. We're taking a bunch of a countable number of open disks and removing them from the plane. The result is compact and connected. Now, remember, the big theorem in complex dynamics, if the Julia set ever contains an open set, no matter how small, by Montel's theorem, that open set grows, and becomes a whole plane. So if the Julia set ever contains an open set, it's going to be a whole complex plane. Well, this Julia set isn't a whole complex plane, because we get the basin, we get the trapdoor, so the Julia set can never contain an open set. That means the Julia set's no other hints. Now, remember, all the critical orbits here eventually land in the trapdoor and go to infinity. They all lie in the basin of infinity, so that means that there's no critical orbits in the Julia set. The map of the Julia set is what we call hyperbolic. And when that happens, the Julia set is automatically locally connected. So cool, just like that, proving 4 of those properties is trivial. Okay, the only thing we have to do is show that the boundary of these regions are simple closed curves that are pairwise disjoint. Okay, we know that the Julia set is locally connected, so we know the boundaries of these curves are locally connected. What we just have to show is that they're actually simple closed curves. That takes a little bit of work to do it. But then it turns out these simple closed curves can't ever meet at some point, because if two simple closed curves met at a point, that meant that junction point would actually be a critical point, and we know the critical points are moving off to infinity. So 4.5 of these properties are easy to show, and then the Julius saturation is confirmed. Okay. Now, a couple of facts. We know that if you take two maps drawn from the same Shapinsky hole, they have conjugate dynamics, the same dynamical behavior. But if you take two maps drawn from different Shapinsky holes, okay, then they may or may not have the same behavior. But in fact, we know exactly when that's the case. Here's the case where the parameter plane where n equals 4, escape time 4. There's 24 Shapinsky holes here that have escape time 4, but only the colored ones have the same dynamics. And only ones that are symmetric under rotation by a third root of unity, like these black holes. These all have the same dynamics. Or symmetric under rotation by a third root of unity in complex conjugation, like these white holes. Complex conjugation and rotate by a third root of unity. Only those symmetrically rotated holes have the same dynamics. You can easily prove that. Okay. If you go to n equals 4, escape time 12, turns out there's only 402 million plus Shapinsky holes. Okay, sorry, I meant to indicate exactly where they are, but I didn't have time. Then we know there's exactly 67 million conjugates of classes. These are a good idea of what's happening in these Shapinsky holes. Okay. And then just quickly, there's all sorts of other ways that these Shapinsky curved Julia sets arise. For example, if you take a buried Mandelbrot set in this picture, choose a parameter from the main cardioid, that Julia set's a Shapinsky curve. Now you see some big Mandelbrot sets, they're not buried because they touch the outside, but if you zoom in on that region there, you see a little buried baby Mandelbrot set. Choose a parameter from its main cardioid, Julia sets a Shapinsky curve. You now see some black regions in there, that's because we have an attracting cycle whose boundary, whose base and boundary is a simple closed curve that's disjoined from the trap door and the base and again, a Shapinsky curve. And if the parameter lies at what we call a berry point of a Cantor necklace, again, the Julia sets a Shapinsky curve. Need not go into details, running out of time. Look at this region here, magnify it. If you look right along this axis here, you can actually see what we call a Cantor necklace. There's a big disk here, flanked by a pair of disks, flanked by a pair of disks. It's basically like take the Cantor middle third set and remove those open intervals that you've thrown away, take those middle thirds and replace them with these Shapinsky holes. Okay, now along this line, we've got a Cantor set. Choose any buried point in the Cantor set. That's a parameter whose Julia set is again a Shapinsky curve. Looks very different from the previous two, but still only one coverage. And finally, there's actually a Cantor set of circles in the parameter plane on which each parameter corresponds to a Shapinsky curve. Right? There's actually infinitely many curves here. Okay. Each curve doesn't pass through these Shapinsky holes, it's completely separate. You choose any lambda value on one of those curves, again, the Julia sets a Shapinsky carpet. But again, only those that are symmetrically located have the same dynamics. So you have a continuum of different, dynamically different Shapinsky curves. All sorts of ways that these Shapinsky curves arise in these families. So, let me just mention one thing. Like I said, all these Julia sets are the same tautologically. They're homomorphic carpets. All very different from a dynamical systems point of view.
Conjugation full atmosphere only on the Julia.
On the whole Riemann sphere. Yeah. No, you can just talk about it just on the Julia set as well. Okay. So the problem is, we know they're all, which ones have conjugate dynamics, which ones don't. The idea is to figure out why certain of these Shapinsky curved Julia sets have the same dynamics and why they don't. Okay, so we want to classify the dynamics of these things. And this was actually done for the escape time Shapinsky curves by Wanner. halfway down here now with her guns, but if you want to see it, I'll show you. I think she did that for escape time. She gets the curves, but there's all sorts of interesting curves that rise. What makes them different? We don't know that. Okay, so I started with one theorem. I'd like to end with a corollary. Yeah, these topologists are pretty crazy. What they look at every day is just a crazy set, but I sure wish I would know that. Anyway, let me stop there. Thanks a lot.
Any question?
What is happening when you guys in satellite software?
In satellite what?
Satellite software, not the main code.
Okay, if you take a very Mandel set with a small, very another Mandel set inside a period of 3 year 20 thing, choose a parameter inside the main category there. You get an attracting cycle of some period, but the bases are disjoint. So still, Stravinsky curve is. It's only those Mandelbrot sets that are, we saw some big Mandelbrot sets that are attached to the outside. If you chose a parameter from the main cardioid there, then the boundaries of the bases would touch. And that can't happen for Stravinsky curves. So those are very different kinds of sets.
Do the Sierpinski curves that appear for the parameter lambda depend continuously in the Hausdorff metric? They move continuously in the Hausdorff metric?
Inside any of those?
Yeah, inside of those.
In those Stravinsky, yes,
Yeah.
they depend, they will depend continuously. I mean, what happens to the Hausdorff dimension there, we don't
Also,
know.
yeah,
That's different. What we do know, for example, is when n is 2, that's so much, in case n equals 3 and higher is much easier than n equals 2. What we've shown is when n is 2, as the parameter goes to 0, lambda goes to 0, so we're approaching the Julia set of z squared. But in fact, the Julia sets converge in Hausdorff topology to the full unit disk. Think about that. The Julia sets are getting, the complements are getting smaller and smaller and smaller as lambda goes to 0. You're getting closer and closer to the full disk. Converges to the full disk. But in fact, when lambda is 0, you just get a unit circle. Disk. So what's happening to those Stravinsky curve Julia sets? Well, they look, ones they're very close. There's all kinds of very close. Very close to 0. They're very thick. What's happening here? Measure the regularizer or Hausdorff dimension.
I mean, you have this family of Jordan curves that are the boundary of holes. How are they determined by the dynamics?
Well, all of them are eventually mapped to the trapdoor and then the base of the thing. So all, for example, of these 6 here are mapped right there and out. On either side of these 6, you'll see, I think, 18 or whatever, all of those are mapped to these guys, then to the trapdoor, and out. So they all eventually map to the boundary of the base of the thing.
And they go back, they are like an expanding map.
Well, no, they don't come back.
I don't.
No, because this is invariant. This curve is invariant. That's the boundary of the base of the fin. All points here go to the fin. Here, the map is like 0 again. So they never come back. There's all sorts of stuff inside. It comes back, but not those things.
What do you mean by varied Mandelbrot?
Well, basically, any Mandelbrot set that doesn't touch the exterior. These Mandelbrot sets touch the exterior. It's commonly meant to do. But if you look closely, right there, you see the little black region? That's a Mandelbrot set again. It doesn't touch the exterior. That's a very Mandelbrot set. Choose a parameter in the main cardioid right here, or in one of the satellite Mandelbrot sets. Choose sets of
But the school, if you choose a comparable parameter in any program,
No, not at all. If you choose a very Mandelbrot set, choose this one, which means that's the Sierpinski curve. Because, remember, if you've written the entire array, you've got an attractive, say, fixed point, a period point, whose boundaries are simple closed curves. But if I chose a point in there, you'd see a quadratic like Julia set, which is the bacillica. The Fatou set is infinitely many pieces that touch each other. So now you should basically curve. Same thing up here, you get a rabbit, you get the main body and 2 ears attached. So the Fatou component would be bounded by simple closed curves when they touch. So not Sierpinski pole. Sierpinski pole, the external regions have to be bounded by simple closed curves that do not touch.
So that is really your proof of that any Mandelbrot set is generated by a normal polynomial like nice, which is secant your
Yes, I mean, the way we prove that this is a Mandelbrot set is by polynomial like a theorem of polynomial like maps. I mean, that's too difficult to get into. But it's actually sort of easy to prove that there's infinitely many of these here via that theorem. Carlos, did you?
Yeah, I was wondering the classification problem.
What problem?
The classification problem
Yeah.
is actually a combinatoric problem, right? Or is there any other ingredient of it?
Well, we know that the only ones that have the conjugate dynamics are those that are symmetrically located by n-1 first rotation unity of complex conjugation. I mean, that's easy to prove by some just basic work with Kevin Hilton and I. I mean, that's easy to prove. And it follows that any non-symmetrically located one necessarily have different dynamics. But the big problem is what makes those dynamics different. That's what Monica answered for the escape time Sierpinski curves. But there are all these other Sierpinski curves, why we do it.
But my question is the answer only comes in terms of combinatoric?
Yes.
It's a combinatoric problem, right?
Yeah, exactly. I mean, combinatorics by rotation by symmetry, and then the dynamical behavior is sort of combinatorics, sort of symbolic dynamics.
Any other questions? If not, we thank the speaker.
Un anuncio.